everyone. In this video, we are going to be looking at forces and motion. So to start with, let's look at what a force is. So the force is a push or pull that is acting on an object. And usually we have force arrows to indicate the forces and its direction. So force arrows, like the arrows that we introduced when we were talking about velocity, the size of the arrow represents the magnitude of the force, so relative magnitude of the force, and then the direction of the arrow is indicating that we are the direction of the force, essentially. So if we are pushing something, then the direction of the force is going to, like, let's say if we are pushing this block of rock, then the direction of the force is going to go to push the rock, if that makes sense. So we're not thinking about it in terms of where the rock is going. We're thinking about it in terms of the direction of the force that is applied. So we can see that over here. This is the force applied on the object. And when we were looking at the idea of net force, it is the sum of all the forces. So you can imagine that if we have, again, a wood block, we have two parallel forces acting on it, then that means that the two forces are going to be added. So this is addition. And that means that the net is going to equal to force 1 plus force 2. If we have an equal force acting on opposite directions, then it's going to be a subtraction. So this is a force, and it doesn't have to be equal, by the way. So if we have force 1 and then force 2 acting on opposite direction, then we are going to be taking the differences. So in this case, the net force is going to equal to the differences. So we'll just say 1 minus 2. So this is resulting in a cancellation effect. And that's saying that we have a force. So again, a block. We have a force that is acting diagonally. Well, we can analyze this force to say that we have a portion going horizontally and then another portion going vertically. And then the vector sum of this is the diagonal force. We are not going to encounter that much for this class, but I just wanted you to know that force can be evaluated even if it is applied in a diagonal way. And the tail of the arrow is the place on the object that feels the force, and then the arrowhead is the direction in which the force is exerted. So again, that is just something that we talked about before. And the length of the arrow is proportional to the strength. So there isn't an exact measurement, but you can see that down here, this one is obviously a stronger force than the one over here. So this is just, again, the force arrows. So there are 4 fundamental forces that cannot be explained in terms of other forces. And these forces include the gravitational force, which is the mass interaction between all objects in the universe. So this is all objects in the universe, between all objects in the universe. So between ourselves and the Earth, between Earth and Sun, between the planets in the solar system, and then this force actually holds the stars together to make our galaxy. So that is gravitational force. We're thinking about large scales. Switching gears, let's look at electromagnetic force. This is acting between electrically charged particles. So this is at the atomic, if not subatomic level. And then this is, let's say, for instance, we have the electrons and proton interaction within the atom, and that is just how small of a scale we're looking at. So these are electrically charged interactions. And then this is electromagnetism, is electricity and magnetism. So that's two things in one word. The third one is the weak and strong force. So the weak force is involved in certain nuclear reactions, and then the strong force is involved in close range holding of the nucleus together. And in general, the strong nuclear force between particles inside the nucleus is about 100 times stronger than the electromagnetic force, and then 10 to the 39 times stronger than the gravitational force. So that is just a quick scale. So this one is 100 times stronger. So this is the strong one. This is the weaker one. And then the strong nuclear force is, again, 10 to the 39th times stronger than the gravitational force. Again, this is the strong one. This is the weak one. So just think about it in terms of like the strength of the force. It is not necessarily the size of the object, but we're looking at force itself. So let's look at how horizontal motion and force can be related to each other. So we can imagine a ball that is just rolling and minding its own business. So it is at constant motion, meaning that right now it has constant velocity. However, when it is rolling, there are a couple forces that is exerted on it. First is the air resistance. And then we also have the friction from the floor. So these two arrows are represented over here. So that means that as the ball is constantly moving forward, there's actually a force that is exerted on the opposite direction. So we can see that these two forces adding up together, we have a net force going to the left. So in sum, this net force is going this way. So it is going to slow down the motion because we don't have a continuous push. So it's going to slow down as the ball rolls forward, right? You can imagine that the ball that is rolling on the ground, eventually it's going to slow down and reach a stop because of the air resistance and the friction of the floor. And because we don't continuously apply a push to it, that's why eventually it's going to slow down, even though it's still moving forward. And note that the arrows over here, this is a force arrow, even though it is moving in direction. So this is a direction of motion. So it's still going forward, it's just slowing down because the force is acting on the opposite direction of the motion. On the second case, again, we have a ball that is rolling on the ground. In this case, instead of letting the ball roll freely, we're going to apply a force that constantly pushed it. So we are going to apply a force. And you can imagine just someone over here is just pushing it as it goes. Okay, so this is the force that is applied. And originally, the ball is moving this way. So this is the direction of the movement. I'll just write it here. Direction of movement. Okay, my handwriting, but that's okay. That way we won't have to disturb it. So we are pushing it, but at the same time when we are pushing it, we also have air resistance, which is the one over here. And then also we have the floor friction, which is the one over here. So we'll have to sum up all these forces that is acting on the ball in order to evaluate how the ball is going to move. So in this particular case, well, we can see that the air resistance plus the floor friction is going to cancel out with the force that we applied to it. So you can see that they cancel out. So the net force force is going to be 0. Meaning that at the end of the day, there's no force acting on the ball. So the ball is going to continue its direction of movement at constant velocity. So it's going to keep going to the left at constant velocity. And you can imagine that if we have a third case. So these two cases are this one. So if we have a third case where we are again rolling the ball, which I'm not going to draw again. We're rolling the ball. I'm just going to modify this one. We're rolling the ball, and I just say that 3 times. And we are experience air resistance as well as floor friction. However, this time we are pushing the ball a lot harder. So the force applied is much bigger. In this case, you can imagine that we have air resistance, floor friction, and then a very big force applied. So the net force that is on this ball is going to be this much to the left, right? It's going to be this much to the left. And in this case, since there are force applied, then the ball is actually going to speed up to the left. Speed up when moving to left. And up here is the case where we are slowing down and reaching a stop. But then we're still moving to the left. It's just we are moving slower and slower to the left. Okay. So this is how force and motion can be related to each other. So let's look at the idea of inertia. So inertia is the tendency of the object to remain in unchanging motion. So whether it is resting or constantly moving at the same velocity with the absence of an unbalanced force. And the unbalanced force is previously when we said that the net force, so F net is force and then subscript net. So that's net force is not equal to 0. That's when we say it is an unbalanced force. If you see someone saying it's balanced force, then that means that the net force is equal to 0. So let's look at the satellite. So in this case, this satellite, it is moving at constant motion with constant velocity. So if no unbalanced force is applied, then it's going to keep going at the same velocity. In the first case, you can see that, let's just say we can go in air and push out a satellite. Why not? So in this case, we can see that we push the satellite from right to left. Then it is going to slow the satellite down, right? Because we are applying a force that is opposite to the direction as to where the satellite is moving. So it's going to slow it down, eventually reach a stop, and maybe you will be able to change the direction of the satellite. Let's just say we are talking about a very, very powerful being that can do that. And in this case, well, we're applying the force that is the same direction as the direction of movement for the satellite. So this can potentially speed the satellite up, right? Because, well, it is moving this way. We're applying the force the same way, so it's going to add up. And in this case, you can see that the satellite is moving this way, but then our force applied is this way. So we can change the direction as to where the satellite is traveling. So basically, when we push it up, it's going to go out of orbit and then go somewhere else. So that's the idea of inertia. If we don't touch it, it's going to keep going and minding its own business because we're in space and there's no air resistance like previously. Previously, the ball rolling on a table, we assume there's air resistance and there's also friction. But a satellite floating in space, there's no air resistance or friction. So we're going to assume there's no force acting on it until we try to push it, do whatever with it to make it speed up, slow down, or change direction. So, okay, I'm just going to write this down just in case. So this is going to slow down, speed up, and change direction. And remember that in all the cases, our satellite is moving from left to right in motion. So let's talk about another case when we have falling objects. So the velocity of the falling object does not depend on its weight. So the velocity of the falling object does not depend on its weight. So any differences between the freely falling bodies is explained by the differences in air resistance. And when the objects are falling towards Earth without air resistance being considered, they are said to be in free fall. So we only look at gravity and we're neglecting air resistance, which is actually going to be most of the case when we are discussing in this class. It's just because that way we can isolate the concept of gravity and discuss that one. So let's relate the idea of distance, time, velocity in an object of free fall. So remember, free fall is no air resistance. So first of all, like we talked about before, velocity is increased at a constant rate. And then a falling object, it is accelerating towards the Earth. So these two things we know. So that means that there's a uniform acceleration, and this uniform acceleration is a result of the force of gravity. So then we have something that is called the acceleration due to gravity, and this is a constant number. This number is always going to be 9.8 meters per second, so you will also see it written as meters per second square, or it is 32 feet per second square. Oftentimes, because it is such a constant that we use very often, we identify it as lowercase g. This g represents the acceleration due to gravity, and on Earth, it is 9.8 meters per second square. So every time you see g in the equation, we know it is this number with that particular unit. So then let's look at how distance, time, velocity can be related in an equation. So previously, we learned that velocity, average velocity, is equal to distance traveled over time. And then, if we have an object of free fall, it has a uniform acceleration motion. So that means that we can also calculate average velocity in terms of Vf plus Vi divided by 2. And this is because it is uniform acceleration. And if you are wondering what I'm talking about, remember to review back into when we are looking at velocity. So that means that with these two, we can rewrite this portion of the equation into something else. So we can say that d over t is equal to Vf minus Vi divided by 2, because both is equal to the average velocity. Then let's try to clean this up. So first thing is, when we are in free fall, that means that we are holding a ball, going to the air, and then drop it. Well, when we are dropping it, that means that the initial velocity is 0. And in fact, all the free fall objects has the initial velocity equals to 0, because they start at rest and then they drop it. So first thing we know, Vi equals to 0. So Vi equals to 0. So that means that we can simplify this equation, so that way it's d over t equals to Vf, because Vf minus 0, this is 0, divided by 2. And we can write it in terms of distance by multiplying both sides by t, so that way these two t can cancel out. Then from here, we have d equals to vf divided by 2. Now, let's look at it in terms of acceleration. So then, for acceleration, we know the equation for acceleration is vf minus vi divided by time, again. And in this case, because we are looking at free fall, so our vi is going to, again, equals to 0. So that means that this term is going to equal to 0 again. So this is going to equal to vf over t in free fall. And that, we can rearrange it in terms of vf by multiplying t on both sides. So we can say that in free fall, vf equals to a times t. And again, I want to stress this 5 million times. We are looking at the case when it is free fall. So it's different from the horizontal motion or any other motion that we were talking about. So now we have an expression of vf. We have the expressions for distance. Now let's just substitute it in here. And from there, we can get that d equals to, we subtract vf with a times t divided by 2. Oh, and at the beginning, I hope you already noticed it, but I forgot a t over here because there's a t here. Sorry about that. So then it's equal to vf, which is a times t, this is vf from here, times t, and then divided by 2. The second t is this t over here. So then we can conclude that distance of the free fall is equal to acceleration times t squared divided by 2. Or you can see people write it as 1/2 at squared, where d, remember, is distance, and then a is acceleration. Okay, acceleration. T is time, and then vf, velocity. Okay, I'm not going to write those down because they are not inside the final equation that we're looking at. But hopefully you can review and then get that the v bar is average velocity. Okay, I'm going to still write it down just in case. Velocity, and then d is distance, t is time, and this is final velocity, and this is initial velocity. So first, the two most important assumptions that we made over here is first, because it is uniform acceleration, we can say the average of the velocity is equal to vf plus vi divided by 2. And then the second thing we know for free fall is vi equals to 0. And then we derive the equation at the end of the day. So with that in mind, let's look at the example over here. So in this case, it says that the rock that is dropped into a well hits the water in 3.0 seconds. Ignoring the air resistance, how far is it into the water? So first thing, we'll again start by making a list of what we know. So we know that it is 3.0 seconds into the water, so the time is 3.0 seconds. We are wondering how far it goes. So that means that we are looking at the distance. We know for a fact that the acceleration for free fall is equal to gravity, and that is 9.8 meters per second square. This is a constant that we know in all the cases when we're looking at free fall. So in this case, well, we are going to use the equation distance equal to 1/2 at squared. And we don't need to solve for the equation because distance is already by itself, right? So let's try to do the math part. So d is what we're looking for. And if you don't like d, you can put it as x is equal to 1/2 times a, which is the gravity g, that is 9.8 meters per second square. And then multiply by time squared. So it's 3.0 s squared. Solving for this, well, again, we are going to separate the numerical part and also the unit part. So the numerical part is 1/2 times 9.8 times 3.0 square. This is the number part. The unit part is going to be m over s squared from here, and then s squared from the seconds. So multiply by s squared. So remember that in the case over here, when we say 3.0s squared, that means that we are squaring the 3, so that's 9, also squaring the s. So the square applies to both of them. And in this case, we can see that, well, s squared and s squared can cancel out because 1 is at the bottom of the fraction. And then we can get, multiplying those three numbers together, we get it is 44 meters, which the unit makes sense, right? Because we're looking at distance. So the last type of motion that we are going to be discussing is the projectile motion. And sometimes you can also hear it referred as compound motion. So both of them are the same thing. I'm just going to write it over here, compound motion. The projectile motion, it describes the type of motion that occurs when we are throwing something. So something is being thrown or projected into the air. So two key things that we need to pay attention to. First, the gravity is acting on the object at all times. So there's a downward force being applied at all times. And then the acceleration due to gravity is independent of any motion that we may have. So remember, this acceleration of gravity is a number that is constant, meaning that it's not going to change as long as we are on Earth. So this number is not going to change, and therefore it is going to be independent of all the other things that we are trying to do for the object. So then let's look at the vertical projectile. So for a vertical projectile, well, we can see that we can imagine that we are throwing a ball upwards and then it's going to come down, or and this is free fall, dropping it from the top to the bottom. So the first stage of this is going to be climbing. So when we first throw it upwards until the max point. Well, as it is climbing, there is going to be a constant force of gravity. And this constant force of gravity is going to result in a reduce of velocity. Therefore, the overall acceleration going upwards is that it is decelerating, which is going to slow down the ball as it moves up until an instantaneous stop, because it's slowing down. And at this instantaneous stop, then that is when we are at the top, then all of a sudden velocity is equal to 0. And then it is going to start falling down after we reach the top, and that is going to be the last stage when we are moving back to surface. So when we are moving back to surface, then we can see that, well, it is just like when we are dropping a ball. We have a constant gravity that is acting on it. So again, we still have a constant force of gravity. And in this case, because it is the same, the force is going this way, the movement of the ball is also going to this way. So it is going to slowly increase the velocity. And this is going to result in acceleration. So in the first stage, when it's climbing, the reason why it is decelerating is because, well, our force is this way, our gravity is this way. So this is our force, this is our gravity. So you can see that those two is going to start canceling out, resulting in it slowing down. So that is vertical projectile. Now let's look at the case when we have horizontal projectile. So basically, there is going to be a force of gravity that is accelerating the arrow downwards. So let's look at this archery. So as the arrow is moving forward, we have a constant force of gravity that is accelerating the arrow downwards. And this is going to result in because it's accelerating, right? So our velocity going downwards is going to increase. So the velocity going down is going to increase. So we can say that the vertical velocity, so the velocity of the vertical motion is increasing. And that is represented by the larger arrow pointing downwards as we go. The second portion of this entire graph is the direction going from horizontal. So in this horizontal motion, there's no force on the horizontal direction if we ignore the air resistance. So that means that the velocity is the same, right? Because there is no force. So the velocity is the same, meaning that our velocity of the horizontal motion is the same. And this is represented by the same size arrow going from left to right. So first, this is describing this motion, and this one is describing the motion that is pulling you down. And those two forces act together is going to result in the arrow landing on the ground eventually, right? The arrow is still moving forward, but then the gravity is going to pull it down. So that's why at the end of the day, the arrow is going to fall to the ground. It is due to gravity. So we can ask ourselves, well, when there's no air resistance, is the arrow going to be dropped at the same time if we shoot it out or if we just airdrop it? The answer is going to be yes. They will hit the ground at the same time, because they are both affected by gravity, right? Gravity is pulling, and then it's pulling harder as time passes by, and then another big arrow passed by. So if there's no air resistance, they're going to be dropped at the floor at the same time, just because the downward acceleration is the same for both of them, which is gravity. So with that idea in mind, thank you for watching this video, and I will see you in another one.